Hello everyone, welcome back. Finally we are in a state to start talking about quantum gates. Uh, you know about classical gates, right? Classical gates like NOT gate or AND gate or gate XOR gates, stuff like that, right? You have some classical bits, and then you apply some operation on that, that is some gate, and then you get some new logical consequence, right? So this is very important to implement algorithms and to literally perform any computation, right? So we need gates, and so similarly we need quantum gates to uh, use a quantum computer, to be more specific, right? So quantum gates are actually unitary operations. Okay, if you remember that we need unitary operations to preserve the norm and the angle between vectors, right? So they are unitary operations, and they are all given. I will introduce you to some very common quantum gates, and you will be needing them throughout the course. So please try to memorize, and we will write everything in the standard basis, in the computational basis. That means in the 0, 1 basis. Okay, so we will write everything in this basis, So the first and one of the most used gates in quantum computing is called a Hadamard gate. Okay, so you can obviously see, just a second, you can obviously see that your unitary operations will be matrices, right? So your gates will actually be matrices. So if you want to act on a qubit is a two-dimensional column vector, right? So if you're acting on a two-dimensional column vector, your 1-qubit quantum gates will be a 2x2 matrix. Okay, so your Hadamard gate is defined by the following matrix: 1 by square root of 2, you have 1 1, you have 1 minus 1. All right, so what does it do? Let's check what H does if it acts on 0. All right, so I teach you how to do this. It's 1 1 1 minus 1, and you have this 1 0 there, because 0 is just your ZGate is represented like this. Okay, so if you want to calculate this, you see that your new state will be 1 by square root of 2 1 1. All right, so what is this state? Can you guess it? I think you can, or you can see it more explicitly. It is 1 by square root of 2 0 plus 1 by square root of 2 1, which is nothing but the plus state. Okay, so you can similarly check that H acting on 1 should give you, you can easily verify, it will give you the minus state. All right, so you can see that there are two results, that H maps the 0 state to the plus state and the 1 state to the minus state. So this is like a basis transformation, right? You're from the computational basis, you go to the diagonal basis, right? And now let me introduce you to some more gates, and this is called the ZGate, or you can call it quantum NOT gate. Okay, so what do you expect from a quantum NOT gate? In a classical NOT gate, what you do, if you have a 0, it will give you 1, and if you have a 1, it will give you 0, right? So if you want a classical, if you want a quantum NOT gate, then you want your 0 to be mapped to 1 and your 1 to be mapped to 0, right? And how can you find that matrix? you can find that matrix like this. I mean, if you want 1 0 and you want a 0 1 here, right? Because you want your 0 to be mapped to 1. So what kind of a matrix do you need here? Where do you need a 1? So you want to multiply this but give it here, right? In the downstairs. So you need a 1 in this corner. Okay, so I don't know about and. Obviously you need a 0 at the top. That means that you need a 0 here, right? So this gives you the first column, and you can calculate the second column in the following way, that you want this, and you want a 1 here, so you have a 0 1 and you want it to be 1 0. So you want this one to go up, this one to go up here, then you need a 1 here, and then you want the second one not to contribute, so you want a 0 here. So we have finally found the quantum NOT gate. So the X gate, or the quantum NOT gate, is written by the following way: 0 1 1 0. Okay, so what does it do? X acting on 0 gives you 1, and X acting on 1 gives you 0. All right, so there is another gate here which is called the Z gate or the Z gate. The Z gate. So this is somewhat like measures the parity of your system. For example, what do you mean by parity? If you have the 0 state, it's even parity, right? If you have a 1 state, it's odd parity. So what kind of a gate you want? So if you act on Z, if you act on 0 with Z, you want to just get 0. But if you want to act on 1, you want to get a minus 1 times 1, because you want to calculate the parity, and the parity of the state is odd, so you need a minus sign before it, right? So what can be the gate? Yes, you can calculate it like before, and what you'll see is that Z gate can be written as something like this. Okay, similarly you can define a Y gate. A Y gate, Y is defined as Zx. That means this is a matrix multiplication between the Z gate and the X gate, or you can check that this is equal to minus the other way around. Okay, and if you calculate the matrix element explicitly, what you get is 0 1 minus 1 0. So I give you this task that you check what happens when you act on 0, what do you get, and if you act on 1, what do you get? All right, you check it explicitly, and I hope you can find it out. And you can also check what you get when you act on Y with plus, Y with minus. Okay, what do you get? So I hope you can calculate it by yourself. And in general, X gate on a qubit K can be written as something like this: K XOR 1, or this means that, okay, this is a sum modulo 2. That means if your K is 0, then 0 XOR 1 is nothing but 0 plus 1 mod 2. So 0 plus 1 is 1, and if you do a mod 2, you have a remainder 2, has remainder 1, right? So 0 plus 0 XOR 1 is actually 1, and if your K is 0, then it will be if K is 1, then it will be 1 XOR 1, and 1 plus 1 is 2, and you do a modulo 2, so you get a 0. Okay, this is how you calculate this XOR. All right, and so this is how you write the operation of x in general, and for z on k can be written as -1 to the power k, and you have this k. Okay, so in both of these cases k can be 0 or 1. All right, so you can check these explicitly, and I'll introduce you to one more 1 qubit gate, which is the phase gate. And phase gate. So the phase gate is defined like this: p theta is 1 0 0 e to the power I theta. Okay, so what does it do? Let's say you start with a vector like this, 0 plus 1. If you act with a p theta, then you'll get 0 plus e to the power I theta 1. So it gives you a relative phase in the one part, right? I mean the coefficient in the coefficient of the one vector. So this is the idea, that you can give relative phases, and okay, these relative phases, that means that it has some phase compared to the 0. These relative phases are important when you are calculating quantum interference and those things, but that is a bit more advanced. But just to let you know that if you have some e to the power I theta, this is called a phase, and it gives you some properties that can be detected via interference or something like that. Okay, so we have been talking about a few 1 qubit gates throughout this video. So first we started with Hadamard, then we had X, then we had Y and Z, and now we have the phase gate. So these are the gates that we have talked about, and I hope that you understood, and it will be very important for you to memorize these gates, because it will be used like almost in every algorithm we do in the future. All right, so thank you so much. I hope you enjoyed the video. Thank you.